Hello everyone. After we already learned three confidence level, the confidence level for the mean when sample standard deviation is known, when population standard deviation is known, and also the confidence level for the mu when the population standard deviation is unknown, and also the confidence level for the proportion, for the population proportion. Now we want to go a little bit of detail on one specific scenario. That is when our population have some special characters, which is finite or infinite. So as we know, all the population is not, we cannot say the population are infinite. They always have a cap, right? So if we think about US population is large enough, regardless, still have a cap. So here when we talk finite, infinite, it doesn't mean, hey, do we have a cap on our population? It is relatively to our sample. We will give a term about our population, whether they are infinite or finite. And why it's important? Because if we consider our population as infinite, and then if that's the case, our sample will not be able to represent the population well, right? Because they're infinite, considered relatively too large. However, if we consider our sample size is really large enough, let's say you have 100 people in the population, you surveyed 80 people, right? You pretty much cover everybody except left 20 people out, right? So that in that situation, your sample size is large enough, and then maybe in that scenario we consider your population is finite, and then we are able to say our estimation is more accurate now because we're including a lot of sample that is cover a large portion of the population. So here we want to focus on, hey, what is that the threshold when we are consider our sample size is large enough, or the other side means we have a finite population, or when we will consider our population is infinite, so that our sample doesn't really able to capture a lot of variability from the population, right? So that is what we are focusing on, is when we are able to determine our population is finite and when it is not, when it's infinite. And after that, we're going to look at, okay, let's see, our population is finite. We consider as finite population. Is there anything we can do with our three confidence interval we already did? Because if we do have finite population, that means our sample size is large enough, and then maybe we need to make our confidence interval a little bit narrower, right? Because we are able to get a more precision on our estimation, our intervals. Okay, so let's look at first when we are able to consider our population as finite or not. If the sample size n is less than 5% of the population, and we are sampling without replacement, then we consider the sample size, the size of the population, to be effective infinite. So basically, when you have 1,000 as your population, and then you surveyed 1,000, let's say 10. Okay, you only surveyed 10. So 10 divided by 1,000 give you 0.001, right? It will be 1%. So you only survey 1% of your population. So even you do without replacement, that means your sample size is large enough because you sample less than 5%. So you are facing an infinite population situation. However, if your sample size n is greater than 5% of the population, let's say you have 100 in your population, and then you survey 50, so then you got 50%, right? Your sample size equal to 50%, and then you do that without replacement. So in that scenario, we consider you have a finite population. So when you have a finite population, that means the marginal error on the interval estimate is actually less than when the sample size is small relative to the population size. Because think about, you pretty cover everything from your population. If you do 50 out of 100, and then without replacement, that means you can do the sample twice, right? Because without replacement. So as you can imagine, that two sample give you is all the information you can get from your population. So your interval should be narrower based on the finite population, because your sample information give you more accurate, more precision, right? So as we sample more of the population, we get more precision estimates. We need to account for the fact that we are sampling a larger percentage of the population. So therefore, the formula, we already learned the three formula we are learning, need to be corrected if we have a finite population. We want to make our interval a little bit narrower by implementing this called a finite population correction factor. So before we look at this formula, I want to re-emphasize, in order to use this FPCF, you want to double check your sample is at least is larger than 5%. Your sample size is larger than 5% of your population size. Okay, if that's the case, you should apply this finite population correction factor to your formula, and also make sure you know it's a without replacement situation, right? Larger sample size without replacement. Okay, so how this formula look like? So it is equal to square root, and n is your population size minus the sample size, small n, and then divided by population size minus 1. Okay, take apart square root. So that is called a finite population correction factor, FPCF. Okay, FPCF. So now let's look at how can we incorporate this to the 3 interval formula we already learned if you are facing a finite population. Okay, so what we're gonna do is add our marginal error, which is after the plus minus sign, and we just need to multiply what we already have by square root of n minus capital N minus small n divided by capital N minus 1. So that's what we're gonna use for our finite population correction factor. Okay, it's very straightforward. First, we need to decide, are we facing a finite population? If that's the case, we just use the formula we already learned, and then make sure instead of just use the marginal error we already have, using the marginal error we already seen times square root of n minus n divided by n minus 1. Okay, we're going to look at an example together and to make sure you know how to use this factor. So Sterling Pharmaceutical has a staff of 1,000 employees. The Human Resource Department sent a survey to a random sample of 75 employees to estimate the average number of hours per week its employee used the company's on-site exercise facility. After you read this case, you should start documenting the numbers. So the Sterling Pharmaceutical has a staff of 1,000 employees. So that's going to be my population number. Why is that? Because it's literally how many employees they have, total 1,000. Okay. So now the second number we saw on this case is 75. A random sample of 75 employees to estimate the average number of the hour per week. So therefore that 75 employee is my sample size, 75. Okay, so in order to decide if we need that correction factor, we need to determine if this 75 employee consists of more than 5% or less than 5% of our population. So so that is one question. Okay, we'll keep going. So the sample results show the sample mean. Okay, use the on-site exercise facility, right? On average, is equal to 3.5 hours. So based on that 75 employees data, we figure out X bar equal to 3.5 hours, and the sample standard deviation equal to 0.83 hours. Okay, so here and we are calculating confidence interval for the mu, right? The mu is the X bar, the mean, given we don't know the population standard deviation. Therefore, we got S instead of sigma. So like I said, first thing we want to know if we're going to use our correction factor, finite population correction factor, we need to look at if the 75 employee are more than 5% population or less than. So therefore, I'm using 75 divided by 1,000. That gives me 7.5%. So that is larger than 5%. Okay, that is larger than 5%. So therefore, we are facing a finite population situation. And that means we do have large enough sample size. Therefore, we need to reducing our marginal error. So let's first calculate our FPCF, finite population correction factor. We directly apply the formula using 1,000, which is the population size, minus 75, the sample size, divided by the population size, 1,000, divided by minus 1, and taking the positive square root, and we are able to receive 0.9623. Okay, so that is 0.9623. So sometimes a student might ask, hey, Dr. J, you didn't explain how this formula coming from. Again, one more time. We are at on-the-level learning, so the only very important thing is remember, this is the formula we're going to use, and when we use it, once you are able to get in more advanced statistics class in the master level, and you are able to learn the underlying reason how we getting this correction factors. So at this point, don't worry about it. Okay, but you definitely need to remember how this formula should look like and how to apply it to calculate the R factor. Okay, so after we calculate the R factor, so now we can apply that factor to help us calculate the confidence level for the mean when our standard deviation, population standard deviation is not known, right? So since the standard deviation is not known, we are using the T statistic. Also, since this is not related to any binomial distribution about the number of success or proportion, so therefore we are using the second formula here, right? The second formula here, because instead we know sigma, we know S from the sample, so it's estimated. We're going to use the T statistic and apply this formula to calculate our confidence interval. Okay, so based on the T statistic from the Excel, and we are able to obtain 1.993 is the T statistic we're going to use. And then the degree freedom, remember, is n-1, since the sample size n equal to 75, minus 1 gives us 74, right? So the X bar here, the sample mean we already given 3.5, and plus minus the T statistics times the finite population correction factor, yes, 0.9623, and multiplied by the standard deviation from the sample divided by square root of n. Okay, so when we use the so that is how we are. When we chose the minus sign, that will give you a lower boundary. If we pick the plus sign, that will give us the upper boundary. Okay, so this is gonna be the more accurate confidence level since we consider population as finite. I also show you the scenario is when we forget about adding that correction, right? If we forget about adding that correction, as you can see, it will be 3.5 plus 0.191 or minus 0.191. So our marginal error is very obviously become much slightly smaller when we apply our finite population error correction factors. It's the marginal error is 0.184. When we forgot about adding that, our marginal error is 0.191. By adding this finite sample correction factor, and we are able to show our interval is more precise, right? Precise. Why is that? As I already explained it. So if your sample size is large enough, cover a lot of more population, you know that you are more likely getting more accurate population parameters value, right? So therefore, when you know the sample size population is finite, after you apply this correction factor, your interval will become much narrower. Okay, much narrower. Okay, so that is the end of this video, and we're going to look at more example in the computer skill lectures to look at how we use the Excel to help us to do the calculation for this kind of problem.